In our previous video, we looked at systems of linear equations. They were equations of m equations of n unknowns. Here we have 2 equations, 3 unknowns. We talked about how if the system is linear, there are only 3 possibilities for solutions. Either we have infinitely many, no solutions, or 1 unique solution. There's no such thing as 3 or 4 solutions. It's either none, infinitely many, or 1. We used matrix notation to simplify our representation of the system of equations. And last, we started solving linear equations using the strategy of trying to get into this upper triangular form where everything under the diagonal, this main diagonal, would be equal to 0. In this video, we're going to look at an efficient way of solving these linear equations. We'll look at echelon form, the formal definition of echelon form here, and we'll talk about reduced echelon form. With that, we'll define what a pivot point is, and then also how we can determine if there actually is the existence of a solution once we have something in reduced echelon form. And last are the steps to solving just a very systematic way of solving a linear equation. And one last comment about this section, really the only thing we're doing in this section is row reducing these matrices so then we can solve the equation. And the row reduction, many teachers don't even teach this because they feel like it's distracting, and what you do, because it is very time consuming, and what they do instead is they just have you go online to these matrix solvers and they'll row reduce the matrix for you. You enter the matrix, it gets row reduced. So how important this is to your class is up to your teacher. We've looked at this informal definition of the echelon form, which is the upper right-hand staircase / triangle. So I said we wanted things in this form where we have this triangle and this staircase along the diagonal, everything below is equal to 0. The formal definition says, first, that all rows consisting entirely of zeros are grouped together at the bottom of the matrix. Here our matrix has no row of completely zeros, but if it did, the zeros would be at the bottom. The first, counting from left to right, going this way, non-zero entry in the I plus first row. So let's just take this as our I plus first row, the second row. Must appear, and let's see, the first non-zero entry is this yellow one in the I plus first row. So that's this yellow that I circled, the number 1. And this number 1 must appear in a column to the right of the first non-zero entry in the ith row. So here's the first non-zero entry in the ith row. And so this entry must appear in a column to the right of this entry. And it does. It's in the second column instead of the first column. And now we take our third row as our I plus 1 row, and the second row as our ith row. Here is the first non-zero entry for the I plus 1 row. Here's the first non-zero entry for the ith row, and you can see this non-zero entry appears to the right of this one, which is exactly what this is asking. And finally, for the fourth and third row, you see that this condition also holds. This last condition, first we need to know what a leading entry of a row. The first, counting from left to right, non-zero entry is the leading entry. So where are our leading entries? These are our leading entries. So this last condition to be an echelon form, all entries in a column below a leading entry are zeros. And you can see that is true. Here's our leading entry 3 and everything's 0. Leading entry, everything's 0 underneath. Leading entry, everything's 0 underneath. So this here is an echelon form according to the formal definition of echelon form. But as you can see, you can kind of look at the requirements and see that they're going to give you this staircase kind of thing. So in practice, you probably won't tick off each of these. You'll just look for this upper staircase. Now that we have the formal definition of echelon form, we can introduce reduced echelon form, which is an echelon form matrix that also has the following properties. 1, the leading entry, remember that's the first non-zero entry in each row, is equal to 1. And we can make that happen by simply dividing each row by the leading entry. So dividing the first row by 3 will make our leading entry 1. dividing this next row, well, we don't need to divide by anything because it's already 1. Dividing this third row by 2 will give our leading entry values of 1. And here we don't have to do anything. Is that true? Oh, actually, we probably should. We should divide this by 4, this row by 4, and so we can get a 1. The next requirement is each leading 1 is the only non-zero row in its column. So here, 1 is the only non-zero row entry in its column. Here we do have a non-zero entry, so we would have to do some elementary row operations to get rid of the 1/3. Here we would have to do some elementary row operations to get rid of these numbers, and as well as here we'd have to get rid of some numbers up here. I will give you an example of how we would go ahead and further reduce this doing this last step here, but before I do that, I just want to give you one more picture of the echelon form and reduced echelon form. And here are the two pictures. These are two echelon form matrices, so you can see the zeros below the staircase and these zeros below the staircase. The boxes, this should be a box, and here we have zeros, are leading entries, and they can be any non-zero value, and they're also known as pivot points. For our reduced, we have two reduced echelon matrices here, and the asterisk are any value including zeros. For the reduced echelon form, we have this idea of a pivot point, which is a location in a matrix A that corresponds to a leading 1 in a reduced echelon form. A pivot column is a column of A that contains a pivot position. So we'll use this example to illustrate this. We're going to row reduce the matrix to echelon form, and then to reduced echelon form, and then locate the pivot columns of A. Our matrix A consists of the row 0, -3, -6, 4, 9. The second row, -1, -2, -1, 3, 1. The third row, -2, -3, 0, 3, -1, and the last row, fourth row, 1, 4, 5, -9, -7. I start by row reducing A, and I notice that this 0 over on top is really unnecessary. So I'm going to move it to the bottom because I can move this 1 up here, which is kind of nice. So I have my 1, 4, 5, -9, -7 now as my first row, and my 0, -3, -6, 4, 9 as my last row. And I did indicate this with this arrow going back and forth saying I swapped the position of R1 and R4. And now looking at my definition of a pivot, that corresponds to a leading 1 in a reduced echelon form. Well, this 1 is going to stay, which is kind of why it's called a pivot, I suppose. And this will be a pivot column. Next, I want to bring my zeros underneath my pivot. So to get zeros in the second row, I'm going to replace R2 with R2 plus R1. So I can just add these two together, and I get 0, I get 2, 4, -6, and -6. Next, I want a 0 in this column, in this position, where the -2 is, so I'm going to replace R3 with R3 plus 2 R1. So multiplying by 2 here and adding, you can see I get my 0. Multiplying by 2, I get 8 minus 3 is 5. Multiplying by 2, I get 10 plus 0. Multiplying by 2, I get minus 18 plus 3, which is minus 15. Multiply by 2, I get minus 14. Minus 1 is minus 15. There is one more thing I need to do before this is an echelon form. Excuse me. I need to move this row of zeros to the bottom. Now my matrix is an echelon form, so now I want to do row reduced echelon form. These are going to become my pivots then. My first non-zero, my second non-zero, and my third non-zero, but I need them to be equal to 1. So I need to divide this whole row by 2. Fortunately, that's easy to do. So I get 0, 1, 2, minus 3, minus 3. I need, oh, this isn't bad either, to make this my 1, my leading entry needs to be a 1, I need to divide everything by -5, and I get 1 here. So this is my row reduced echelon form. My pivots are here, which has remained a pivot. This was always going to be a pivot position, but just in case, I'm going to circle it again to remind myself it's a pivot, and you can locate your pivots after you do the whole echelon reduced form. And the last pivot point then is going to be here. So we have 3 pivot points. So I've been solving these equations for you, kind of explaining what I've been doing, but there is a systematic set of steps that you can use. So I'm going to use this example here as an illustration of this systematic way of solving systems of linear equations. The example will be the system of 3 equations, 5 unknowns. And the first equation is 3x2 minus 6x3 plus 6x4 plus 4x5 equals -5. The second equation is 3x1 minus 7x2 plus 8x3 minus 5x4 plus 8x5 equals 9. And the last equation is 3x1 minus 9x2 plus 12x3 minus 9x4 plus 6x5 equals 15. And the first step is to begin with the leftmost non-zero column. That looks like the leftmost, this looks like this one. And this is going to be our pivot column. And the pivot position is at the top, which actually is not at the top now. So select a non-zero entry in the pivot column as a pivot. If necessary, interchange the rows to move this entry into pivot position. So that's what we did here. We interchanged row 2. Oh, actually, for whatever reason, I selected row 3. We interchanged row 3 and row 1 and made this our pivot. So now our matrix is 3, -9, 12, -9, 6, 15. That's our first row. Our second row stays the same, and then our first row moves to the bottom, the 0, 3, -6, 6, 4, -5. Okay, so the next step, use row replacement operations to create zeros in all positions below the pivot. So we want zeros. Well, there's a 0 here, so we just need this to be made into a 0. So we add R2 minus R1, and we get a 0 in this position here. Looking over here, so we've created zeros in all positions below our first pivot. So now we're going to cover or ignore the row containing the pivot position and all rows above it. And we're going to apply the previous step to the submatrix. So we're going to ignore this row and all rows above it, and we're going to just look now at this submatrix here. And then we're going to repeat our steps. So we begin with the leftmost non-zero column, which is this -2. That's going to be our pivot column. And the pivot position is at the top, which it is at the top of the submatrix. So if necessary, so we don't need to interchange the rows because it's already at the top. Use row replacement operations to create zeros in all positions below the pivot. That would be this position here at 3. So we're going to replace R3 with -3/2 R2 to create the 0 here. And you'll notice now we're in echelon form. Now we come here, repeat until there are no more non-zero rows to modify. So we've modified all the rows now, and we're in echelon form, so we're ready to go to our next step. Beginning with the rightmost pivot, create zeros above each pivot. So the rightmost pivot, so beginning over here. But the other thing, I think you can do this first, and I like doing this first because it gives me smaller numbers. Make each pivot equal to 1 by scaling. So here I've divided the first row by 3, and I divided the second row by -2 so that I get my 1s at my pivot points, and now I have smaller numbers to work with. So the other thing you need to do is create zeros above each pivot, right? We already did zeros below each pivot in these steps to echelon form, but now we need zeros above. So this one's good. Here we need to create a 0 at this -3 point. So we're going to replace R1 with R1 plus 3 times row 2 to get this to become a 0. And now why did I have this? Oh, I'm sorry. So then my next pivot point, so I have zeros above this pivot point. Now I have this pivot point here, and I need to create a 0 at this position at 2. So I'm going to replace R1 with R1 minus 2 R3, and I get a 0 here. And now I'm at reduced echelon form. To solve the equation now, I'm going to label my columns. So this is the column associated with the coefficients x1. This is the column associated with the coefficients for our second variable, x2. Here's x3, x4, x5. And our solution, well, we've been modifying it, so it's no longer -5, 9, 15, but it is -24, -7, and 4. So I can start reading off. x5 is equal to 4, and I always go from the bottom up. x5 is equal to 4, and then here, well, I don't have anything about x2 and 3, but I can solve for x2 in terms of 3, 4, and 5. So x2 is equal to my minus 7 plus 2x3 minus 2x4. Then my x1 is going to equal to minus 24 plus 2x3 minus 3x4. What I have is x3 and x4 are free parameters, and I have x1, x2, and x5. Well, x5 is fixed at 4, and x1 and x2 are solved in terms of x3 and 4, are parameters. And so there are an infinite number of solutions, because for different values that you choose for 3 and 4, for every set of values you choose for 3 and 4, you're going to get a new set of solutions. And just to kind of check to make sure our answer is sort of reasonable, or get a little more faith in our solution, we should choose some easy numbers. I might choose x3 equals 0 and x4 equals 1. Actually, gosh, these numbers are kind of big, the 24 here. Anyway, I'm going to choose x3 equals 0 and x4 equals minus 1. So x1 is minus 24 plus 0 plus 3 is minus 21. And x2 is going to be minus 7 plus 0 minus, or plus 2 now, is minus 5. And x5 is equal to 4. I'm going to plug these numbers into my 3 equations just to make sure I have something reasonable. And so I plugged my numbers for x1, x2, x3, x4, and x5 into my equations, and I did verify that I get these solutions. So this is, the answer is probably correct. I probably should have also tried x3 and x4 equals 0 and plugged that in, because those are easy numbers, but it looks like it looks all right. Probably, actually, I should have gone the other way around. x4 equals 0 and x3 equals 1. I shouldn't keep making x3 equals 0, because that doesn't test out the x3 portion of it. Anyway, so this is kind of my sanity check on my solution. This next problem is to find the general solution of the linear system whose augmented matrix has been reduced to this echelon form. So we can go ahead and do back substitution. That is, I would start with x5 equals 7. Then I have here x3, or 2x3, is equal to 3, moving this over to the other side, 8x4 and x5. And then my x1 is equal to minus 4, moving this to the other side, we get minus 6x2 minus 2x3, moving to the other side, we get 5x4 and 2x5. So from here, I can see that I have 3 free variables, because I've only defined 3 variables here. So x2 and x4 are free. I guess actually, I'm sorry, x3 is not free. I have that x5 is equal to 7. So x3 I can solve as 1/2 3 plus 8x to the 4th plus plugging in the 7 for x5. So this is x3 in terms of our free variables. And then x1 is equal to minus 4 minus 6x2 minus 2 times x3, which I plug in here, what I've already solved for in terms of x4, and then I get 2 times x5, which is 14. So now I can solve x1 in terms of our free variables. So this would be the solution. Again, this is working with the echelon form, but since we're also talking about reduced echelon form, I'll go ahead and reduce this to echelon form as well. And now I identified my pivot points. That's where my leading entries are. And the first thing, I have this in echelon form. To get in row reduced, would begin with the rightmost pivot, which is this one, and create zeros above each pivot. So I need this row, this -1, and this -2 to be 0. To get this -1 to be equal to 0, I'm going to replace row 2 with row 2 plus row 3. And this is what I have. And now I need this -2 in row 1 to be equal to 0. So I'm going to replace row 1 with row 1 plus 2 R3. And this is what I get. So I have, so far I have 1, 6, 2, minus 5, 0, 10 for the first row. Then 0, 0, 2, minus 8, 0, 10 for the second row. And the last row is 0, 0, 0, 0, 1, 7. So now this first pivot column has been taken care of. So I'm going to the next pivot column, which is here, and I need to make this 2 in the first row equal to 0. So I'm going to replace row 1 with row 1 minus row 2. and this is what I get. So now all my pivot columns are taken care of. They're zeros in everywhere except the pivot position. And the last thing I need to do is make each pivot equal to 1 by scaling. So just this row here needs to be divided by 1/2. And one last comment before we move on to the answer. Often I said that I would scale first before creating zeros above each pivot. So it doesn't matter what you do first, but the reason I like to scale because that gives me smaller numbers, but the reason why I didn't do this first on this example is because I could see this 2 and this 2 here would be really easy to cancel out and get a 0 here. Also this -1 and 1, that made these two rows easy to add together. And the last reason is if I divided everything by 1/2, I would have a -1/2 and 3/2, and then I'd have these fractions, and that would have been ugly when I started adding rows. So I declined to scale it until later. If you recall last time, when everything in the row was divisible by 3, or it was all divisible by 5, so the scaling was quite nice, no fractions. So I have my scaled matrix here, and I label my columns. This is the column associated with x1, the first variable, the column associated with second, third, fourth, and fifth variable, and these are my solutions. So I have the first equation here says that x5 is equal to 7. My next row tells me x3 minus x4 is equal to 5, or in other words, x3 is equal to 5 plus x4, 4x4, sorry. And then my last row, my first row tells me x1 plus 6x2 plus 3x4 gives me 0, or in other words, x1 is equal to minus 6x2 minus 3x4. So we have the same variables, 1, 3, and 5, and then we have 2 and 4 are free. And if you check, this is the same solution we had when we did the back solving for the echelon form. And we did test one set of solutions. I think x2 was equal to 0 and x4 was equal to -1 or something. And we found that there was one solution. And whatever values, each time you choose different values for x2 and x4, you'll get a new solution. So since there are infinitely many choices for x2 and x4, there are infinitely many solutions to this system of equations. And there were a couple of theorems that I did want to also point out to you. And the first one is uniqueness of the reduced echelon matrix. So each matrix is row equivalent to one and only one reduced echelon matrix. And 2, the existence and uniqueness of solution. So a linear solution is consistent or has solution if and only if the rightmost column of the augmented matrix is not a pivot column. That is, if and only if an echelon form of the augmented matrix has no row of the form of all zeros except with B in the solution column. And that is it for this video. Thank you for watching.